Hi guys, welcome back to AP Calculus. Today we're going to take one step closer to making those rectangles and those sums of all those rectangles into integrals and how those two things are related. All right, so last time we were making area formulas or finding area under the curve by adding up a bunch of rectangles. So now what we're going to do is, instead of having the rectangles each have a width of like a half or 0.4 as we had it last time, we make that width really, really small. And that width is what we call delta x. If I can find my pen here, there it is, delta x. That is the width. All right, and the height, so here's our width. The height is the function value. All right, so each one of these is the area of a rectangle. Right? And we're adding up a bunch of these rectangles from 1 to n, or from 0 to n minus 1. So we're going from 1 if we're doing the right-hand rectangle. We're going from 1 to n. If we start at 0, we're doing the left-hand rectangle. It's not really a big deal most of the time, because if we take the limit as n goes to infinity, it takes care of it. It doesn't make much of a difference, but that is how it works. So if we add up all these rectangles, or an infinite number of them that are infinitely small, or infinitesimally small, we should get almost the exact area. All right, so the way we find the delta x is we do what we did last time. We do the length of the interval and divide it into n rectangles. So divide it by n. In each rectangle, we start from our starting value a, and then we add to it a delta x times I. So if we start on the left, we're not adding anything to it. If we start on the right, we're adding one width to it. So we'll start on the right side of the rectangle. So for instance, find the summation formula for the area under the curve f of x equals 4 minus x squared between x equals 1 and x equals 2. And we'll just do this one from, say, the right. So we can start with 1. So we're going to have the limit as n, and not x. So used to writing x. It's been so long. N goes to the infinity of the sum. I get lazy when I write these. I don't make them look perfect. The sum from I equals 1 to n of this function. Well, let's take it one step at a time. So we need to find delta x. So delta x will be 2 minus 1 divided by n, or 1 over n. And we need to find what this c sub I is going to be, where we want to plug in each one. So it's going to start at 1, and we're going to have plus delta x times I, like that. So in other words, we would have f of 1 plus 1 over n times I times our delta x, which is 1 over n. Now, instead of just writing this with f, we're going to plug in our actual function here. So we'd say that this is the limit as n goes to infinity of the sum I equals 1 to n of, it's going to put it like this, 4 minus this whole thing, 1 plus 1 over n times I. I can just write that as I over n squared times 1 over n, like that. All right, and that is the summation formula for the area under this curve between 1 and 2. And if we could sum that up, that would give us the exact answer. We're not going to try and learn the formulas for how to sum this up. They do exist. They are out there. We could do that. I did that when I took calculus, but I'm not going to make you guys do that. All right, so for this one, let's go ahead and start on, let's switch colors here, and we'll do this one from the left instead of the right. So since I say we're going to start from the left here, that means we're going to do the limit as n goes to infinity still. Our sum is going to go from 0 to n minus 1. And we've got our function g of, well, we need delta x. So delta x is 6 minus 2 over n, or 4 over n. And we need to know what we're going to plug in. What's our endpoint, c sub I? Well, it's going to be a, so our starting value here is 2, plus 4 over n, delta x, 4 over n, times I. So we're going to have 2 plus 4 over n times I, times our delta x, which is just a 4 over n, like that. So we get that this is equal to the limit as n goes to infinity of the sum from 0 to n minus 1 of, and now we just plug it in. So instead of g, I'm going to say, well, it's the square root of 2 plus 4 over n times I. If I want, I can put the I up there with the 4. And then outside the square root, we've got the delta x, which is 4 over n. All right, and there's our answer. So now we should be able to go forward and backward here. So we should be able to look at this and say, okay, well, there's multiple ways you can write your answer, first of all, but say maybe we start here. This is our a. This is definitely our delta x at the end here. So that means b minus a over n equals 4 over n. So that means b minus a equals 4. And if we're starting at 2, we'd get b equals 6, a equals 2. So we're going to go from 2 to 4. And it looks like our function is the square root of a plus delta x times I. So it looks like our function here, which I guess we were using g, is just the square root of x. So we should be able to go forward or backwards doing this. All right, so these have a fancy name. They are called Reimann Sums, named after the guy who came up with them. I believe he was German. So if we let f be defined on a closed interval from a to b, for any partition of a, b, where all these x's are between a and b and all of them are not equal to each other. So like we keep going up just a little bit more. This is like maybe these are our right-hand rectangles or maybe these are our left-hand endpoints, whatever. Where delta x is the width of each of these, so each one has a width of delta x. They could be different widths too. All right, so they don't have to be the same width. Maybe this one's 1, maybe this one's 2, maybe the next one's 0.5, whatever. If c sub I is any point in those I intervals, then this is our Reimann sum. Usually we take the limit as n goes to infinity, and that gets us the exact answer. So this could be right endpoints, this could be left endpoints, we could use midpoints, all right? We could use the quarter point, any point you want for this c sub I, as long as it's in the interval. All right, so now we take the limit of that, take the limit as we go to infinity, and we say that that is equal to, so notice it does say equal, not even approximately, equal to the integral from a to b of f of x dx. So that's how we say this. This is the integral from a, the lower endpoint, to b of f of x dx. And that integral is exactly equal to the area under the curve between this function and the x-axis. All right, this is called the definite integral because it has a defined start and end point. Start at a, end at b, of f from a to b. The number a is the lower limit, the number b is the upper limit. All right, the definite integral finds the area bounded by the function and the x-axis. So the area between the curve and the x-axis. Some weird things can happen here. Area below the x-axis is negative area. Area above the x-axis is positive area. So like this would be positive area, this would be negative area. All right. If f is continuous, then f is integral. All right. So if it's continuous, we can take its integral, we can find its area. We have problems when we have asymptotes and jumps and things like that. All right. So write each of these definite integrals as a Reimann sum and then find the area. So there's a couple, I haven't shown you how to actually take the definite integral yet, but we're going to use other techniques here. So we're going from a to b. So a is -2, b is 1. So that means our delta x, which is the first thing we do when we try and find this, is 1 minus -2 over n. So that's going to be 3 over n. Our c sub I will be, well, we're starting at -2. We're adding 3 over n times delta x, or times I. And our function is just what's in here. So our f of x is 2x. So if we want to write this as a sum, this would be the limit as n goes to infinity. We can do right or left. So let's just go from 1 to n. That's usually the way we do it. Of 2x with this plugged in for x. So 2 times -2 plus 3 over n times I times delta x, so times 3 over n. So there is our limit as, or there's this integral as a limit of a sum. All right, so this is our 2, this is our x, this is the dx part. So this is really, and this is the integral sign part. That's kind of how it lines up if you want to think about it that way. Now, if we want to find this actual area, well, let's take a look at the graph. 2x is just a line. It has a slope of 2. We're going from 1 to negative 2. All right, so this would be 1 by 2, and this would be 2 by, if we plugged in negative 2 here, that would be negative 4. So this area, 1 times 2, half of that, because it's a triangle, would be 1. This area is negative 4 times 2, so it's below the axis, it's going to be negative. So it's negative 8 divided by 2, so it's negative 4. If we add up these two areas here, we get that the area is negative 3. Just adding those up. 1 plus negative 4 equals negative 3. All right, next one. All right, so our function is this guy in here. So we'll say our f of x is the square root of 4 minus x squared. Our delta x goes from, let's see, here's a, here's b. So we're going from 2 minus negative 2 over n. So that's 4 over n. Our x sub I, or our c sub I guess, sorry, c sub I is what we were using. We're going to use, we're starting at a, so negative 2 plus 4 over n times I, delta x times I. There we go. And now we're going to write it as a limit. So we say the limit as n goes to infinity. We'll just go ahead and start at I equals 1. I, not n. And we'll go to n. And now we're going to plug this into our f for x. So I'm going to try and do this all in one step here. So it's going to be 4 minus this whole thing, negative 2 plus 4 over n times I squared. And then outside of the square root, so we'll close the square root here, times delta x, so times 4 over n. So that means this now is equal to this. If you look, so like here's the function part, there's our f of x. And here, at the end here, there's our delta x or our dx. And this is kind of works as our integral sign. Actually, it's all this kind of together works as our integral sign. All right, but now how do we find this area? All right, well, I haven't shown you how to take this integral yet. In fact, I don't know if we're going to learn how to take this integral. That's a tough integral to take. But if we just look at the shape, it's not a tough shape to find the area of. In fact, we should know that that is just the top half of a circle. Like if we set it equal to y, square both sides, move the x over, we get x squared plus y squared equals 4, which is the same thing as 2 squared. So this is a circle centered at 0, 0 with radius 2. Like that. So this is just the top half of a circle, right? It was the positive square root. If we had a minus the square root, it'd be the bottom half of a circle. But now we just want this area in here. So the area here is 1/2 pi r squared. So it's going to be 1/2 pi times 2 squared. 2 squared is 4. Half of 4 is 2. So we get 2 pi. So this whole stuff is actually equal to 2 pi. Same with this integral, 2 pi. All right, so that is how we write integrals as Reimann sums, or definite integrals as Reimann sums. And so definite integrals find areas. Reimann sums also find areas under the curve. We'll put it all together and we'll actually show you how to do it with integrals next time.